today we're going to be talking about using mine tailings to remove carbon dioxide out of the atmosphere and turning mine tailings piles into carbon sinks. And so pose the talk as a question because there's two sides to it. There's the science behind why mine tailings are such a promising target for this purpose, and but then there's the other part about implementing it at scale. And so I'm going to be talking a bit about our journey towards commercialization, how we are trying to do that. Just gonna try to get the slides moved. Do I have to turn it on? Yep, perfect. And so I've split the talk into three main sections. So first we'll kind of go through the big picture, why we're talking about this question. Then want to talk about the research coming out of our lab at the University of British Columbia. Our lab is led by Dr. Greg Dipple. We'll talk about the geology, mine tailings, and then what we've been doing to try to accelerate the rate of carbon mineralization for carbon dioxide removal. And then finally, I want to share what we've been doing and how we decided to build a company that's called Carbon Minerals. And we'll talk about what led to that and how it began and how it's going. So we'll just start out with a snapshot of some numbers. I think some of these numbers will be pretty familiar to folks in this audience. You know, we're at 419 ppm CO2 in the atmosphere today. I remember in my undergrad, I was using 350 in equations, and that really wasn't that long ago. We're at 1.01 global temperature rise since the Industrial Revolution. And maybe some of these other numbers aren't quite as familiar, but we know what they mean. These numbers translate into real dire effects, flooding, wildfire, increasing frequency and severity of extreme weather events. And we've all felt the effects, but I do want to point out that it's the most vulnerable populations of our society that are feeling these effects the most, and it's those people who've contributed the least to the problem and have the fewest resources to deal with the impacts. So looking into the future, we'll stick with the numbers a little bit longer. 1.5 degrees is basically the threshold after which our planet becomes a much harder place to live. And that's been determined by the IPCC and others. And so what this graph is showing is our emissions, carbon dioxide emissions on the y-axis over time. So we see our historical emissions in black, and then various scenarios looking into the future. So those red lines, that's a scenario of kind of business as usual, continuing upon our current trajectory and with some of the more formidable temperature rise. It's that blue line at the bottom that that's what we need to hit to meet that 1.5 degree target, or even 2 degrees. And so you will notice that that blue line goes below 0. And so now we're talking about negative emissions. So what that means is we need both reductions and carbon removal. We cannot do one without the other. We need both. So we can all say this with BART. We need both carbon removal and decarbonization. So this may be a newer term to some of you, but carbon dioxide removal, and I'll be calling it CDR probably throughout the presentation. It's the capture and storage of CO2 from air such that the net effect is a reduction of CO2 content in the atmosphere. And there are, it's a pretty nascent field. The technologies to do this are early stage, and you know, we're trying to reach about 5 to 10 billion tons of carbon dioxide removal per year. And to put that in context, probably global capacity right now is in the tens to hundreds of thousands of tons per year. So that's several order of magnitude away from where we need to be in the next couple of decades. And so there are a variety of different types of CDR, which is a good thing because we need all hands on deck. So from the more engineering based, which is your big fans that suck CO2 out of the atmosphere, kind of like your like carbon engineering out in Squamish, or your more nature-based solutions, your forestry and soil amendment technologies. The other important thing is that with carbon dioxide removal, quality matters. And this is talking about, can we store the CO2 for long time scales? Is it verifiable? Is it additional? Can it scale? And carbon mineralization, the thing that our lab focuses on, is a very promising approach because it has virtually unlimited storage capacity. And also, once you mineralize the carbon, it stays there as rock for basically permanent for all we care, but for geologic time. So what carbon mineralization is the conversion of of CO2 into inert carbonate minerals via these aqueous reactions between CO2 and base cations like magnesium. And we like a type of rock called ultramafic rock because it's very rich in magnesium and it provides those base cations. So now we're going to dive a bit deeper into the science and the research coming out of our lab. So I just want to highlight all the amazing scientists who've contributed to this work. So our lab is led by Dr. Greg Dipple over there on the left, and we're supported by many different organizations. So back to the geochemical framework of carbon mineralization. Again, we need a source of these cations, so that comes from mineral dissolution. And then a source of CO2, and that can be either from the atmosphere or point source. We are really focused on atmospheric CO2 in the work that we do. And so together those react and form mineral carbonate. So there are, again, like I mentioned, many advantages as a mechanism for CDR, but it is slow to form in nature. And so when we think about the carbon cycle, we are typically thinking about the short-term carbon cycle, and we think less about the long-term carbon cycle. But over geologic time, there are other processes like chemical weathering that fundamentally control the climate. These processes occur too slowly to impact the carbon cycle on the human time scale, but when you take rocks and grind them up like mining operations do, then you start to see reaction rates increase like 1,000,000-fold, and you can start to affect change on the time scale of the short-term carbon cycle. And just to drive that point home a little bit more about chemical weathering is major mountain building events have been associated with global cooling in the past. So for example, the Antarctic ice cap didn't exist before the Indian plate and the Eurasian plates collided, thrusting up a lot of fresh silicate rock exposed to the atmosphere and consuming carbon dioxide. There's a lot of equations here on the right side of this slide, and we don't need to go into them at depth. These are a bunch of chemical weathering equations. One thing that I want to point out is you can see the CO2 is consumed in these equations. And then secondly, that CO2 can be stored as either alkalinity or carbon mineralization. And carbon mineralization is a subset of chemical weathering reactions. So this diagram is showing a variety of technologies and solutions just around weathering and mineralization. And so there's something called enhanced weathering. which is based on that alkalinity that I was just showing. And we treat that that's a very different end product than your mineralization solution. So they're treated very differently in the CDR world. And there's also, you can have in situ mineralization or ex situ mineralization. And we're focused on ex situ mineralization opportunities provided by mine tailings. This is surface reactions at the surface, whereas in situ is more about injection of CO2. Although I will note that you can inject CO2 into mine tailings as well, and we are looking at both of those. So again, mine tailings, these mines are already in the business of digging up and crushing a bunch of rock. That increases reaction rates and provides feedstock for the carbon mineralization process. And some mining operations, such as nickel, platinum group elements, and diamonds, are typically found in ultramafic rocks. So these are our target mines. And ultramafic rocks are found, they're globally distributed. You can see them in, the ultramafic is in green. So these aren't rare rocks by any measure. And a study by our group looked at the carbon mineralization potential of ultramafic rocks in BC alone. And we found that in the top kilometer of ultramafic rocks, there was 56 gigatons of CO2 storage potential. And that's just in BC. So that's about 800 years of the province's emissions. So there's capacity. We're not in the business of crushing up just any old ultramafic rock. We are targeting mines in ultramafic rock. And for those of you who are interested in the geology behind how these are formed, can form intrusively. Ophiolites are ultramafic. That's when mantle rock is abducted and then exposed to the surface. The biggest example of that is the Oman ophiolite. There are companies that are looking at injecting CO2 into the Oman ophiolite because of its mineralization capacity. There's also komatiites and kimberlites, which are extrusively formed. They're basically old lava flows. And then these different formations are associated with certain metals or commodities. You'll see nickel is associated with many of them, and then diamonds are found in kimberlite. So ultramafic rocks are composed of a variety. It's an umbrella term. There's a lot of different minerals and mineral types and altered minerals in the ultramafic group. The main takeaway from this slide is that there's a hierarchy of reactivity. Some mineral groups are have higher reaction rates than others. And so, for example, oxides and hydroxides have faster reaction rates and lower associated costs of carbon mineralization than, for example, bulk dissolution of silicate minerals, which have slower reaction rates and much higher energy costs. So although the CDR potential is much lower for these, it's a way to get out the door. You can start removing carbon from the atmosphere now by targeting the most reactive minerals. This second row is based on serpentinization, or the hydrothermal alteration of silicate minerals. And when that occurs, you're creating these sheet silicates with high surface area, and you can do non-stoichiometric dissolution that allows a lot more magnesium to be released and provides a huge feedstock for carbon mineralization. So the point is that you don't necessarily need to dissolve entire silicate minerals in order to get to the tens of hundreds megatons CO2 removed, maybe gigatons. And that's these top rows are really what our group is focused on. And it's happening. So this was the observation that Greg and students made a couple of decades ago that mine tailings were taking up significant amounts of CO2 just passively by accident. And so the poster child for this is Mount Keith in these squares, where 40,000 tons of CO2 per year are being uptaken just by accident. So the question is, if this is already happening, what can we do to accelerate it? And that's the focus of the research in our lab. So the answer is there's a lot of things that we can look into. We do accelerated air capture trials, injection of concentrated CO2, activation treatments, finding those most reactive minerals. The deposits are quite heterogeneous, and so targeting the most reactive parts, and the labile magnesium is key. We study natural analogs to learn from nature. And then importantly, we've put a lot of work into building a robust monitoring and verification system. And so we don't have time to talk about all of these, but I'm going to share a few slides about our accelerated air capture trials and our monitoring and verification technology. So again, we are very focused on, our lab group loves brucite. Brucite is a hydroxide mineral. It's magnesium hydroxide. It reacts quite fast. And so we love tailings that have brucite and serpentine. So that's the top two rows of that hierarchy that I showed before. And all of our experiments use tailings or metallurgical samples from mining companies. So we work with FPX Nickel Corp, which has a major deposit in central BC called the Baptiste deposit. Giga Metals has another promising nickel deposit called the Turnagain in northern BC. And then we have worked at the Cassiar asbestos mine in northern BC as well. This is a closed mine. No, we don't, asbestos is not mined anymore, but it's a great place to hold field trials. Lots of serpentine there. So I'm going to show you a few slides about the field trials that we've done and how we've accelerated air capture rates compared to baseline, and then how we monitor and verify that, because otherwise how do we know how much CO2 we've captured? Starting with a benchtop experiment. This is Fran here, a recent master's grad. This is an experiment using FPX nickel tailings. So we have CO2 flux here on the y-axis. So that's the CO2 going into the tailings, being captured and mineralized. Starting with dry tailings, there's no reaction. She adds moisture in the second segment, which helps those dissolution-based reactions. So we see a bit of a jump in the flux there. But really what we want to point out is then she manipulates the tailings. She churns them up to maximize contact with the atmosphere. And we see this major jump in CO2 flux. And then we've put a comparison of what the Mount Keith rate is, just to compare that these rates are, they're 2 to 5 times higher than baseline, and they're also quite comparable to the Mount Keith, quite higher than the Mount Keith nickel tailings. And then we see this in the field as well. Oops. Yep, that's the right slide. I have two computers in front of me. So we see this in the field as well. This is a field trial that Peter Scheuermann conducted. He's a postdoc in our lab and a co-founder of Carbon Minerals, which I'll be talking about. And so this again was using FPX nickel tailings, and you can see flux on the y-axis again. He had a control tote, that's in the yellow symbols here, and then 4 churned totes. So that's, again, he was just churning up the tailings to maximize contact area, and we see this jump in influx of CO2 up as high as 5 to 6 kilograms CO2 per meter square per year, which Again, this is in very unoptimal conditions. This blank spot is because we had snow, which doesn't happen very often in Vancouver. But even so, we were able to get these results. But both of these experiments really were just focused on optimizing that surface area contact with CO2. There are a whole bunch of parameters that we can optimize to maximize the CO2 uptake. So this graph is actually showing moisture content, and you can see that there's a sweet spot at around 8% moisture content in this experiment. And so the idea is that if we can measure and understand these parameters, we can fine tune them and make sure they're all where we want them to be in order to optimize that CO2 uptake. And that's going to be really important for large scale deployment. So I want to talk a bit about our monitoring and verification as well, because all of the graphs that I just showed you have CO2 flux on the y-axis. So that's measuring the gas going into the tailings. One of the nice things about carbon mineralization is relatively easy to monitor because you get this carbonate mineral at the end of it that you can literally hold in your hand. And you can go out and sample that and do total inorganic analysis and then measure the amount of carbon that's accumulated over time. So what we do is we scaffold these different well-established technologies, and we make sure that they align. So TIC is one of them. Dynamic closed chambers here in the foreground. This is a chamber that closes over this green collar and measures CO2 concentration over time to get a flux. And again, that's a pretty small surface area measurement, but it is instantaneous and continuous. And then we have an eddy covariance tower here in the background. And this is basically an anemometer that measures wind speed and direction, and a CO2 analyzer, and a bunch of other weather sensors, and a whole bunch of math and modeling. And it can measure the amount of CO2 flux over large footprints. So now we're talking about square kilometers. And by doing all of these together and seeing if they converge, we can have really confident, robust results. And so I'm going to show you that. This is a graph of, this is Peter again, another air capture experiment that we did. And this is a graph of change in CO2 concentration on the y-axis. And then, so the black line is your flux, measured by dynamic closed chambers with dash bar arrow lines. And then the symbols are the TIC taken at different points in time. We see pretty good alignment, which is pretty nice. And then I'll show you results from eddy covariance and dynamic closed chambers. These are data taken from our very first mine deployment at the Cassiar asbestos mine. That's me, Marty, and Fran, wearing our respirators. Again, this mine closed back in the 90s. So this tailing pile is just sitting there. Any reactive materials would have most likely already reacted by now. So we weren't necessarily expecting exciting results. But what we did do is we measured flux on the untouched tailings that have just been sitting there for decades. And then we bulldozed, not us, we hired someone to bulldoze a pad to expose about 1 meter off the top to expose fresh tailings. And then we set up an eddy covariance and dynamic closed chamber system on that to measure fluxes. And these are those data that we got from the disturbed pad. I'm sorry, I'm switching things up a little here. The more negative is more CO2 flux on this graph. But what you'll see is, again, really good convergence between the two independent measurement methods. So eddy covariance is the black symbols, and dynamic closed chambers is in the gray symbols. And I do want to show you what that compared to against the baseline. So again, more negative, more CO2 uptake. The blue is the baseline, and so we are seeing the new fresh material that we exposed not only up to more CO2, but did it sustained over a couple of weeks. And so that was actually pretty exciting results for us. And the other thing to note is that we took samples, there's no brucite. Again, that's that really reactive material. There's no brucite in these tailings. These are all serpentine. You know, that was another exciting finding from this when we had pretty low expectations. And I'll just show you the numbers. So the data that I showed in those graphs translate into an average baseline flux of 0.2 kilogram CO2 per meter squared per year, compared to a manipulated, the fresh pad that we measured about 4x over baseline. We always love to compare to Mount Keith, which is that's brucite-bearing tailings, and that's 2.4. So comparing 1.1 with no brucite, that's actually really good. So we'll just recap some of the stuff that I just talked about. We have been showing consistently in a whole variety of different experiments from 1 meter squared to 4,000 meters squared that we can achieve 3 to 5 times air capture over baseline. And so if we apply that to a large nickel mine, then we're already in the hundreds of thousands of tons CO2 removed per year. Our monitoring and verification scaffolded system is been shown to be quite robust. We are also working with Uli Meyer at the University of British Columbia to do some reactive transport modeling, using these data to calibrate the model, which is very useful for infilling data gaps, but also forecasting to predict how much CO2 we might be able to remove. And so our next steps are to deploy the churning and integrated monitoring verification system at an active mine at large scale. And that is this right here. So bringing us back to our hierarchy of reactivity, we're really focused again on deploying our ready-to-go technology on brucite-bearing tailings, the most reactive tailings. We are also working on other technologies that are at the lower technology readiness levels. So we're doing a lot of R&D simultaneously to unlock this major feedstock. And so once we bring those up the TRL chain, we hope to add that to our deployment system to maximize uptake. And then there's other researchers working on a variety of other exciting stuff. So Sasha Wilson, Den Wilcox, and yeah, are working on these other pieces. So then I have this question here. How do we move from research field trials to large scale deployment? And the key is mining partnerships, because we can't do what we do without the mines. There are a couple pathways to do this. We can continue to do this as a research group, but another pathway has opened up to us, and we have decided to commercialize. We've spun out a company, and we're building partnerships as a commercial entity now. And that allows us to keep our own IP, develop our technology, and then deploy at mine sites around the world for maximum impact. So let me introduce to you Carbon Minerals, our sort of new company that we incorporated in 2021. This is Peter, Greg, and I co-founded the company, and it was not an overnight decision. There were a few different underlying factors occurring, things that we were observing over the last several years that led to this. And so that's what I want to talk about for the next and final section of my talk. So mainly it was conversations with the mining industry were changing. All of a sudden, decarbonization was top priority. There's this emerging carbon dioxide removal, really looking for mineralization solutions. And then we were getting a lot of inbound interest from VCs, company builders, just investors who are actually just encouraging us to commercialize. So we did. And now Peter, former postdoc, is our head of technology. Myself, a research scientist and manager, head of operations, and Greg, head of science. So yes, like I said, decarbonization was all of a sudden the top priority for mining companies. They're facing various pressures and incentives, investments, and consumers are telling them that this is what they want. But we were also observing this firsthand as a lab. So over the last several years, we've now have contracted with over 40 different mining or mining-related companies. And so in response to, and these are all inbound requests. These are companies contacting us because they want to know if their tailings might have mineralization potential. So in response to the demand, we set up a fee-for-service program in our lab to help these companies understand the opportunities of their tailings. Pretty unsustainable as a lab, so we are transitioning that to carbon minerals. And this is a graph showing why this demand on our lab was occurring. So battery and critical metals are projected to have very high growth in the next couple of decades. So this graph on the y-axis is just an index. So 1 equals the rate of mining today. And we'll take a look at nickel because that's the commodity that we like because it's most often found in ultramafic. And so you're looking at, 10 to 20 times the rate of mining as today going into the future. That's huge. And there's yeah. So these different bars I do just want to point out are different scenarios. So this is the stated policy scenario, but this is the sustainable development scenario. That's why there's quite a difference between them. But overall, demand is high and growth is expected to match. And I'll point out, so that's how we get to gigatons, is that the feedstock for our mineralization process is about to skyrocket. And so we want to be able to work with those mining companies to optimize those tailings facilities for carbon removal. And yeah, so this slide, this demand is also being driven more and more by contracts that require sustainable mining. So this graph, this slide is just showing how Tesla is scooping up contracts directly from the source or contracting directly with mining companies. And Tesla needs to, it's requiring sustainable mining because, for its consumers, they want to know that they're not just moving from fossil fuels to dirty mining. It needs to be sustainable mining. And so that's when the companies that Tesla is making these contracts are with, they're then coming to us to ask us how to do it. How do we decarbonize? Because we have to fill these contracts. So I'll switch now to the emerging carbon removal industry, and what we've been experiencing there is that, so these are not the carbon offsets of the past, which are controversial and problematic for a variety of reasons. These now companies like Microsoft and Shopify, they are seeking high quality carbon removal. So again, that's atmospheric removal, high storage times, verifiable and able to scale. And they're willing to pay for it, and a lot for it. And so we're trying to take advantage of those high prices right now. And not only are they willing to pay for it, they're willing to prepay for it. So Google, Facebook, Stripe, Shopify, they all just made this consortium called Frontier, which has put $1 billion in advanced market commitment to buy carbon removal. And these folks also were reaching out directly to us to see if we had mineralization opportunities that we could submit for them. And then I'll just show you this slide. This slide is taken from our company deck, but I wanted to highlight how big this industry is projected to be. Again, we need tens of billions of tons of carbon removal per year. And so that's translating into $1 trillion industry driven by these corporate net zero commitments and government legislation, which is coming, which is starting, and we expect it to continue. And then, so you have your, what we call the early adopters, that's the Shopifys, but there's a lot of fast followers as well. 3,000 corporations have already committed to science-based targets, which are promoting those criteria of carbon removals. And we're not the only ones responding to this. This figure is just showing companies and startups in the mineralization and enhanced weathering space alone. Startups are popping up all over the world, all over the place, and it's pretty exciting. A lot of these are like us, coming out of academic labs. And it's also been promoted by these patient type of investors. These investors seem to be they are mission aligned, and they're not looking for that 3 to 5 year return. They know that this is going to be a long process. These technologies are early stage. And so that is also enabling all of these startups to kind of get the money up to start. And so all of this was occurring. And so it kind of seemed like we had to do this. And we wanted to do this. So we created Carbon Minerals. Again, we incorporated in September 2021. We got our first investment in December 2021 from the Grantham Foundation, and they also gave us a grant to the lab to develop some of our more early stage technology. But this was crucial because they really pushed us to negotiate with the UBC IP Transfer Office, and so they wanted to make sure that the research in the lab was flowing to the company that they just invested in. So, but that was big for us too, because it really pushed these negotiations forward. So now we have a licensing agreement with UBC so that research from our lab can flow to the company. Oops. Then the next big thing that happened was we had our first purchase agreement. Again, this is a pre-purchase agreement with Shopify. So Shopify agreed to pay us for carbon removal that we have yet to produce. We will be doing that next year, but again, just an example of the crazy industry that we're in. And then right around that same time, we won the X Prize. This is a Elon Musk funded X Prize, and it's the biggest prize in the world, biggest X Prize that's ever occurred. The whole pot is $100 million, and 15 million of that was given for milestone prizes. And we won one of those, catapulting us up into kind of that top tier. Everyone now knows about carbon minerals in the space. So that was a huge development for us. The other thing that we've been working really hard on is our partnerships with mining companies. So luckily we have a really nice base to work off of with those 40 mining relationships with our lab. And Greg has a lot of long-standing relationships from the works that he's done over the years. We have now 3 signed MOUs with top global mining companies, which is looking to translate now into our first commercial pilots next year. And so that's really, this is showing you what has happened over the last year, and where we're going is really focusing on rolling out that first deployment. And it's kind of some of the stuff that I talked about in the earlier part of the talk, what we want to get out and start doing and start learning and start removing carbon. And so it started just the 3 of us, and we built out our leadership team, and we've hired a wonderful R&D team that's actually come mostly from our lab at this point. And so we are growing, and it's been very exciting. And so I just want to leave you with this slide, using minds of the future to tackle emissions of the past. So thank you, and welcome any questions.
Very much, Bethany. So we're going to do the online questions first so that we can then get to the room. First is from Gallagher. Please comment on your plot that you showed earlier on day versus night, the striping of the stripes from a rain event. Why is that?
Yeah, great questions. There's a lot to talk about on this slide, so I skipped over a lot of the details. One major detail that I should have mentioned is this diurnal cycle, and I'm sure you all observed that. Thanks, Tom, for the question. So the gray bars is showing nighttime versus the white is daytime. And so we are seeing effects of temperature and evaporation on our CO2 fluxes. And actually again, because I switched it on you, this graph is showing where negative is higher flux. So this rain event is actually showing more negative fluxes. And so this is where there's more basically dissolution occurring, and we're seeing more uptake during the rain events. And another really important piece to this is that it's so important to have this type of continuous monitoring that we have with EC and dynamic closed chambers, because if you do just take spot measurements at a certain part, you might really overestimate or really underestimate your CO2 removal. So we take continuous measurements to get an average, because we are seeing such a diurnal cycle.
Thank you, Bethany. So another question from attendee Robert Kirby. Thanks for the great talk. Do you know how much energy is required for unit of tailings to dissolve in the number kilograms per meter squared, 1.1 kilograms per meter squared? Does it say how much CO2 needs to be generated by whatever in order to actually remove this amount of CO2? Is there an LCA for the costs?
There is an LCA. There is a techno-economic analysis. I don't have those numbers in front of me. This is obviously something that we keep for first and foremost, and kind of goes back to that hierarchy of reactivity and why we're focusing on the most reactive minerals too, because those don't take a lot of energy to react. Those don't take a lot. So we are focusing on the more low cost group of minerals first. What I don't have the numbers off the top of my head, but you know, from the LCAs and the TEAs that we've done and we've submitted, for instance, that we submitted to XPRIZE, the feedback is that we have a really good ratio compared to other solutions. We don't actually use a ton of energy to remove our carbon. So.
Wonderful. Anonymous attendee asks, is there any application of this technology to Alberta oil sands tailings?
Yeah, good question. Unfortunately not. It's just not the right type of mineralogy. It's very like we have to be in the right type of geology, and the oil sands won't work.
Okay, another one from Gallagher. What is the impact on the water draining through the tailings, hydrologic subsurface waters? Have you sampled these waters? What minerals are leached out and concentrated? Is this like a leaching operation?
I don't know that much about heap leaching, but what I will say is nope. I don't know where the slide is. Oh, this one. No. This one. So when we're working on mine tailings, like if part of the question may be about water contamination, that is very much regulated and managed by the mining company. Like they cannot allow seepage of metals into surrounding water. But what I want to comment on is that, yes, sometimes there is, if the CO2 is caught up is stored as alkalinity and then is kind of exported as alkalinity, it actually takes up 2 moles of CO2. It takes up twice as much CO2 as the carbon mineralization reaction, because in this reaction, you're actually releasing one of the CO2s. So it is really important to make sure that we close our mass balance, and we, the field trials that we've done, we actually haven't been sampling any, or Peter's field trials, actually, yes, he samples the outflow and measures and basically gets nothing. It's mostly all mineralized in those field trials. When we're doing large scale, we do want to understand if there's CO2 storage that's leaving the system as alkalinity or staying as a mineral form, because that will also inform how much CO2 is uptaken. But the nice thing is that if it stays as alkalinity, we actually capture more CO2, but it does then, there are issues of monitoring and verifying that. It's really hard to keep track of.
Thank you. Another question, I think, on that same vein from Ed would say in our department.
Oh, hi, Ed.
Yeah. Is there potential for the enhanced carbon mineralization to result in acid mine drainage issues, which are obviously water quality concern of many mine basins? How would these be addressed?
So the other thing is that we're actually working in very high alkaline systems. So acid mine drainage has not typically been something that we have to think about, because if the material is acidic, it won't really work for carbon mineralization.
Rachel Lauer asks.
Hi, Rachel.
Yeah, another question. Looks like the mixing of tailings optimized CO2 plus with just 2 mixings. Does that depend on surface area of the tailings? Why is that result the way it does?
Which one? I actually don't know how many mixing events he did. He has these 4 different totes, and he treated them each slightly differently. Some were being churned like weekly, some were not being churned as often. And so we are kind of, part of what we're trying to do is maximize how often we churn, because at large scale, that's going to be more cost and more energy to do. So we want to manage that with maximum CO2 removal. But, you know, we usually probably won't like use up all of the reactivity before we churn again. So these are variables and things that we are trying to tune in our process. It's not as easy as just going and churning up a bunch of tailings. So that's again about these different parameters that we're looking at and trying to optimize and maximize. And also that's why our monitoring and verification is such a crucial part of this, because we're doing real-time monitoring and verification, so we can use that data real time to help us understand our uptake levels. Hope that answered your question.
Skylar Lippman asks, how might this impact the permeability of tailings and nutrient availability of these things?
Yeah, I'm not a soil scientist, so I don't know too much about, because we are going to be creating carbonate minerals instead of the ULTRAMAFIC tailings. And so over long term, when those tailings piles are then restored or reclaimed, I'm actually not sure what the effects on nutrients and the soils will be. So that's a good question.
Okay, 2 more questions. First one from Daniel. Okay.
Nice.
what would this look like in an active mine site? So you're doing, I think, a lot of, for example, at Cassiar, ancient or inactive sites.
Yeah.
What would this look like? Is it in the mill, or would the tailings have to be deposited first and then mixed? How does that go?
Yeah, great question. So, in terms of the manipulation work that we do, so that would be on the tailings piles after it's come out of the processing unit. And so that's what we call our drop-in technology. It's pretty unintrusive. We've already gone through a risk assessment with one of the mine companies because absolutely 100% we cannot do anything that interferes with tailings dams. But the other part about working on active mines is that they are actively depositing tailings. So what we go and do is we maximize uptake on CO2 on the tailings that were just deposited, and then they deposit more fresh tailings, and then we go do it again. And so that's why we really like active mines, because they're already doing the work of moving all of that rock for us in their mining operations. We don't have to do that ourselves. So that is what we call, this stuff is what we call our drop-in technology. And then some of the stuff that we're working on that's at a lower, like that's our R&D work at lower technology readiness levels, that might be incorporated into the processing circuit.
Wonderful. So another final question from Tom Gallagher. Are there extra concentrated metals that are concentrated by this operation that are proposing in this potential economic resource?
So not our process, but one opportunity would be to work with companies that are focused on reprocessing mine tailings, because there are still metals in tailings, and with newer technology and AI, there might be some value from metals in tailing files. And then if that's occurring, then we can maybe partner with those guys to implement our technology at the same time, because they're already going to be reprocessing them.
Okay, great. Thank you everyone online for asking such enriching questions. We're going to transition off the webinar. Great. So yeah, now we're closing out the webinar, so you're not being recorded anymore.
Okay.
So anyone in the room, if you have questions, please raise your hand.